You're watching a hurricane peel shingles off roofs, snap telephone poles like matchsticks, and turn brick chimneys to rubble. And then you zoom into a pile of twigs in a backyard tree. 100-mile-per-hour winds howl past it for hours. Not a single egg is broken. A hurricane can crumble reinforced concrete, but a bird's nest, a random, half-hearted bundle of trash and sticks, holds its shape like an earthquake-proof vault. That should be impossible. Yet the secret isn't magic or instinctive engineering. It's a kind of physics we still struggle to fully explain. Today, we stress test the impossible geometry humans can't replicate: stochastic packing and granular jamming. The physics behind how a messy pile becomes rigid under pressure. In the next moments, we'll go from the bird's eye view, a nest beating the storm, down to the microscopic contact points where twigs press, rub, and lock. We'll explain how a non-linear, disordered arrangement turns flexible parts into something that behaves like a solid. You'll meet the jam state, when chaos becomes structure. And we'll point to the exact threshold where loose debris flips into a load-bearing fortress. Finally, we'll show why engineers still can't copy this simple-seeming trick. First, stochastic packaging. Imagine you're making a nest by throwing sticks into a hoop randomly. No blueprint, no bolts. If you place twigs at random, you create a structure that's statistically full of pockets, lever arms, and overlaps. That randomness is the key. It gives you redundancy, multiple overlapping paths that can carry load if one path fails. Disorder, irregular shapes which interlock rather than slip. Non-linearity, small changes in position produce big changes in stability. A nest isn't trying to be efficient, it's trying to be robust. Stochastic packing increases the chance that somewhere in that chaos, there exists a configuration that can resist bending, shear, and torsion. Granular jamming is the physical process where a collection of discrete particles, sand, cereal, sticks, transitions from a fluid-like state, they flow past each other, to a solid-like state, they resist shear, when conditions change: packing density, applied stress, or friction. The jamming transition is not thermal like melting. It's geometric and mechanical. Seminal work by Liu and Nagel framed jamming as a phase-like transition, controlled by parameters such as packing fraction, how much volume the particles occupy, shear, and applied pressure. Experiments with photoelastic disks, Majmudar and Behringer, show force chains, highly localized paths that carry most of the stress, forming exactly when a system jams. Twigs aren't perfect spheres. They are elongated, flexible, and rough. That changes the jamming game. Shape anisotropy. Rods and fibers can entangle and align, trapping neighbors. Flexibility. Twigs bend and store elastic energy, then settle into new contacts. Friction and roughness. Irregular surfaces increase contact forces and resist sliding. Polydispersity. Mix of twig sizes fills space better than identical grains. All of these make the jammed state more stable and hysteretic. Once jammed, the structure resists small perturbations without requiring constant pressure. Researchers parameterize jamming with a critical packing fraction, the density at which particles start to form a spanning rigid network. For simple frictionless spheres, Experiments and simulations report phi-j in a narrow range, the so-called random close packing. But for irregular, frictional, elongated particles, phi-j varies widely and depends on orientation, friction coefficient, and applied shear. Two practical control parameters for nests. 1. Local contact number, the average number of contacts per element. There's a minimum contact number needed for mechanical stability. For non-spherical objects, this threshold is higher and more complicated. 2. Global packing fraction. When enough twigs occupy the available volume, load paths percolate through the structure. When the nesting process, or a wind load, pushes these parameters past the thresholds, the pile gains rigidity. Additionally, shear jamming can occur. Applying a directional load, wind, predator movement, can itself drive a loose pile into a jammed state. Zoom in further. Stability lives at contact points. Each twig contact transmits normal forces and tangential friction. In jammed nests, you see force chains, line-like structures where forces concentrate. They are the scaffolding of the jammed state. Contact networks, a web of nodes, contacts, and edges, force transmissions. The network's topology, loops, branches, redundancy, determines toughness. Frictional locking and mechanical interlocking. When twigs wedge, their geometry prevents sliding even if individual contacts are weak. Think of it like a zipper. Each tooth contact is weak alone, but when many engage, the whole zipper resists a huge pull. Experiments with photoelastic particles reveal that force chains are highly heterogeneous. Most forces go through a small fraction of contacts. Nest geometry naturally produces this heterogeneity, but also redundancy, so if one chain fails, others pick up load. Nests are dynamic. Wind shakes them, rain soaks them. Two important dynamic behaviors. Adaptive strengthening. Cyclic loading can tighten contacts, frictional aging, increasing resistance over time. Twigs also bend into more interlocked positions. Failure modes. Catastrophic collapse occurs if a percolating force chain is broken in a way that disconnects the contact network. But because nests have many redundant paths, collapse often requires correlated failures, like sustained extreme winds or targeted damage. Engineers call this resilience graceful degradation. Partial damage doesn't cause total failure. That's why a nest can lose a few sticks in a storm, but still keep eggs safe. Key empirical work underpins this story. Liu and Nagel, 1998, framed jamming as a unifying concept for disordered materials. Majmudar and Berenger, 2005, used photoelastic discs to visualize force chains and showed how load is funneled into networks. More recent work on shear jamming, B et al., 2011, and follow-ups, demonstrated that directional stress can induce a jam even below static packing thresholds. Studies on rod-like particles and fiber networks show that anisotropy and entanglement dramatically lower the amount of material needed to jam. Together, these results explain why an apparently brittle pile of twigs and trash can behave like a resilient, load-bearing shell when the right statistical conditions are met. Why don't we build houses like nests? Two reasons. 1. Predictability versus adaptability. Engineered structures aim for predictable global responses. Stochastic jamming trades predictability for robustness. It's hard to guarantee which specific contacts will bear load. 2. Control of assembly. Humans build repeatable, optimized structures. Jamming exploits random variability and local feedback. Contacts tighten in response to loads. Replicating that self-organizing feedback at scale without huge safety margins is hard. However, researchers are trying. Granular metamaterials, jammed robotic grippers, and modular shelters that stiffen when vacuum is applied are direct inspirations from jamming physics. So next time you see a nest intact after a storm, don't call it luck. Call it physics. A stochastic, jammed fortress built from randomness and rough contact mechanics. Nature uses disorder as a design tool, something human engineers are only beginning to harness. If you want to see this in action, hit the like button and tell me in the comments which example surprised you most. The force chains, the phase thresholds, or the idea that wind can jamify a loose pile. Subscribe for more videos where we break down wild natural engineering into the physics you can understand, and maybe steal for your own designs. Share this with someone who thought nests were just cozy. They're clever physics. Subscribe, and we'll keep testing nature's impossible tricks.